Hey guys, my name is Chris and my final year project is to build a prosthetic hand which is supposed to be cheap, 3D printed and able to mimic the human hand's movements pretty accurately. So currently it does that. There's a lot of improvements that could be made, but it's able to do 6 degrees of freedom, and and on top of that, for my project I also made a control glove which wraps around my hand and I'm able to control those 6 degrees of freedom of my prosthetic, and that's right here. I also wrote an overview paper on the field of upper limb prosthetics, and it goes through the different types of prosthetics there are, the types of control methods there are, the rehabilitation process and the costs of being an amputee these days, which can be quite expensive. And that is one of the main reasons I'm doing this project, which is to cut down the costs and be able to produce a product that's cheap but also able to mimic things that are also that are high-end and are able to do things that the normal human hand can do, but are very, very expensive. So I started off in my overview paper to go through a whole lot of the literature, and I tried to do that systematically. So I used a program called Confidence. In my paper I started with talking about the rehabilitation process. I suppose not many people realize that there's a whole lot of things involved in terms of costs and administration and the whole process of what happens to you if you lose a limb, and there's a whole team behind you trying to take care of you, so physicians, nurses, occupational therapists. The rehabilitation process has gotten much better over the course of time, and as you can imagine, this sort of thing costs a lot, right? So in the 2012 study there was found that the cost of an electromechanical prosthetic, something like this, can cost you between $25,000 to $75,000, which is a lot of money. And you might think that's it, but there's a whole lot of other costs involved as well. So I guess inevitably I have to talk about the types of prosthetics. So you can classify them in a lot of ways, but the main way I guess you can classify them is in terms of function, or how you use them. And you can classify them into two ways: body-powered prosthetics and electromechanical. So body-powered prosthetics usually use some sort of cable system that you can actuate them. It's a fairly simple thing, but it's one of the most common things. You can also have passive prosthetics, you know, like you see in pirates, they have the hook. They don't do anything, but they're passive. But yeah, body-powered prosthetics can be a variation on that, where the hook can actually move and actuate. Then you get to different, more expensive types of prosthetics, like electromechanical prosthetics, and this is the kind of thing that I built here. And these are actuated not using the body's movements, but using things like motors or other types of actuators. So body-powered prosthetics have been around for a long time. I mean, the pirates have them, so they're generally very cheap these days, especially with 3D printing technology. There are open source projects such as the Cyborg Beast hand, there's the Raptor hand, and these are very rudimentary, basic, easy to assemble. They work with a wrist flexion mechanism, and most people, I guess, are fine with that. But when you get to the higher end, you get to hands that are like the Bionic hand or the Michelangelo hand. These hands are very, very mobile, and you have a wide variety of movement that you can do with these things, especially the types of grips you can do. It's very much like the human hand, and of course these are the most expensive things on the market. So there's a bit of a gap between the hands that are electromechanical, who are able to replicate the normal human hand's motions, compared to body-powered hands, which are very rudimentary, but they're very readily available. So my project is supposed to sort of bridge that gap, make the price difference much smaller. Those are the two types of hands. Obviously there are many other types of classifications. You can talk about different methods of control, and in terms of body-powered control, you have that cable actuation mechanism that I talked about before. You'll see that very quickly that myoelectric control is the sort of gold standard in the field. It basically detects the electrical signals in the actuation of your muscles, and from that you get an electrical signal, and you can pass that on to your motors, and that can actuate your hand. Then you have more advanced mechanisms of control, such as pattern recognition control. Then you have even further invasive techniques, such as targeted muscle reinnervation, TMR, which we won't really discuss. Then you have much newer methods of control that interface with your nervous system, so things that can interface with your peripheral nerves, your arm, shoulders maybe, or things that can interface with your central nervous system, so things that can interface with your brain. But these are like the newest sort of control methods. Either way, my hand is pretty standalone. Generally, prosthetics terminal devices are. They're able to be controlled by a number of control mechanisms, but what the hand does is that it can receive whatever input signal it receives and do the movement it's supposed to do. And for my case, because I couldn't test on a human person, I did make a control glove to do that part. So for different control glove designs that I've seen online and in different papers, they tend to be one of two different types. You can find gloves that use force sensing resistors, which the glove turns out to be very, very sleek and small. The only problem is that these resistors can be quite pricey. You can get maybe one resistor for $30, and when you have 6 degrees of freedom, that's a lot of money. Then you have other control gloves which uses potentiometers or motors, and these can be very, very bulky. So for my design, I thought of doing a simple solution of trying to put rotary potentiometers at the axis of rotation of the fingers, but as you can see, initial designs of mine were very unstable, they were very clunky. So I opted for more of a gauntlet looking solution because it wraps around the fingers and was much more stable. So essentially you have very good actuation of the finger, and that allows you to read the angle of the joint using the potentiometer. And overall the cost of this ends up being around $50. You just wrap the plastic gauntlet around the gardening glove, you can hot glue that on, and it works pretty well. So the current design can measure up to 3 degrees of freedom per digit, and I say potentially because currently the design only measures 1 degree of freedom per finger, because that's what the prosthesis can do, and it measures the angle of the PIP joint. One of the limitations of the design is that it's very hard to make a fist because the components are just too large. So this limitation of not being able to form a fist stems from the fact that the 3D printed components need to be this particular size, thickness, around 3 millimeters. If you're using metals for components, then yeah, you could get away with thinner pieces, and that could allow you to have more mobility when you're using this gauntlet. Another limitation is is the CMC joint. I tried to use this mechanism which has a rotary potentiometer fixed to the palm, connected to a spring, and the other side connected to a wire which actuates when you pull when you rotate your thumb. I chose this design because unlike the fingers, you don't have access to the center of rotation. The CMC joint is a very complex joint, so this is one of the ways I thought would work, but currently it is very prone to jamming up and it's not very accurate, so it really does need some improvement. Other limitations is that unlike other control gloves, this glove cannot measure adduction and abduction of the digits, so that is something that needs to be improved upon in the future. So overall, the design of this glove can be useful for controlling robots who have a prosthesis or some sort of humanoid hand on them. So for the design of my prosthetic, I went for a cable design where a linear actuator will pull the cable and the joint will flex, and once released, the joint will return back to its natural position because there are torsion springs inside the joints. So we can see that more clearly when we look at the construction of the phalanx joints, the fingers. And within this you'll see that the center is a torsion spring, and it's flanked by a rotary potentiometer, and this is the same thing that was used in the control glove, and it measures the angular position of the joint. And on the other side is a ball bearing to reduce friction losses. You can see that when the cable is pulled, the finger actuates, the whole finger actuates. in future it's possible to modify this design so you can have 3 cables coming in, so that when one cable is pulled, each joint can be flexed individually. So when we move on to the construction of the MCP joint, you can see that it's a very similar design to the phalanxes, but the one difference is that it allows for abduction and adduction of the hand. One of the differences between how it works on my prosthetic compared to a real hand is that the fingers abduct away from the pointer finger rather than the middle finger. But this is a design decision that effectively gives you the same functional outcome. So one of the showcases of my project is the CMC joint of the thumb, which is a very complex joint of the human hand. So my design is able to achieve a lot of the movements that the natural human hand can. So you can see how this works by looking at the construction of the joint. You can see that it's a modified MCP joint, but it's slightly bent where the thumb attaches, and it's also connected to the palm component at an upwards facing angle. So this allows it to have the mobility of the human thumb, but it only is 2 degrees of freedom, so you don't have to use that many actuators to get that sort of movement. So overall, the hand is very mobile. It's able to perform a lot of the grips that the human hand can produce, as you can see here, and potentially it is able to have 17 degrees of freedom. I say potentially because currently the design only uses 6 motors to actuate the 5 digits and the rotation around the CMC joint. In future you can add the extra flexion of each joint in the digits, as well as the abduction and adduction of the MCP joint as well. So finally, after hooking up the control glove to the prosthesis and using a very basic PID library from Arduino, so as you can see, I'm able to control the main digits pretty well, even though the ring finger is quite slow in actuation, and because of time constraints I couldn't actually get the thumb working, so you can see it jittering there. It's because there is actually no PID controller that is just trying to get into position by any means. So overall, the results are promising. The project is more of a long-term project because the control glove and the prosthesis can be improved, but right now you can see that the prosthesis is able to mimic the human hand pretty well, and is able to be potentially controlled with that amount of dexterity as well. So I set out to make a prosthesis that was affordable, and currently the prosthesis, it costs around $450, and a majority of that price is because of the actuators. So this is a promising start in producing a prosthetic that is both affordable and able to provide the precision that high-end products are able to produce.